think we're going to move on now to the next speaker. She's Zita Patai. She's a postdoc at the University College London, where she's investigating the neural correlates of navigation in humans. She uses fMRI and MEG, among other tools. And today, the title of her talk is Conflict Detection in a Sequential Decision Task is Associated with Increased Cortical, cortico-subthalamic coherence and prolonged subthalamic oscillatory response in the beta band.
Well, thanks very much, Alex, and thanks for everyone in the Neuromatch community for making this possible. My title is a little bit of a mouthful, but it kind of summarizes it. So if you don't get my talk, you can read the title and get the gist. And normally I would freestyle this, but given the time limitations, I've stuck to a little bit of a script. So no jokes for now. Okay, so we usually explore conflict in sort of these sort of simple contexts. Like here you can see this is called a flanker task, and what you can see here is that the peripheral stimuli are facing the opposite direction than the middle stimulus, and this is what you would call an incongruent trial. And these are sort of termed conflict trials. They're basically when your prepotent response needs to be inhibited to some extent. So these sort of conflict trials have been associated with an increase in theta power. And that's true for the frontal cortex and the subthalamic nucleus, which is what I'll be talking about today. So the subthalamic nucleus has been proposed to be this sort of decision gatekeeper via sort of changes in oscillatory power. Recently, however, there has been some evidence that theta power might also provide information about conflict, but sort of across trials rather than within trials. And there is an increased coherence between frontal cortex and the subthalamic nucleus, but the locus of this cortical coherence is not clear yet. Additionally, most of these studies, and what I'm trying to show here on this little image here, kind of look at conflict on a sort of moment-to-moment basis, rather than looking at it over sort of a long period of time when we accumulate evidence and multiple bits of conflict may come and go, much like in real life. So to study this in more detail, we developed a sequential decision-making task, and it's very simple. Participants are shown cues. There's only two of them. There's either a left-facing mouse or a right-facing mouse that you can see here. And essentially, they're presented these mice in a sort of pseudo-random order, and they have to make a decision about whether they think the mouse will run to the left or the right. So it's just a plain evidence integration task. But importantly, you need to accumulate the evidence over these discrete time steps, and you terminate the search by yourself. So if you think you've accumulated enough evidence, you can make a response. So the reason I've included these ... dots here is because you can take as many cues as you want. You can sample as many as you want. And to study the neural correlates of this sequential decision making, we used 13 patients implanted with deep brain stimulation electrodes in the subthalamic nucleus and whole head magnetoencephalography, as well as 13 match controls who obviously only were in the non-invasive MEG scanner. Quickly, the behavior. Patients obviously worse than controls, but still above chance. More importantly, the interesting thing about patients was that here I'm plotting a histogram of the number of cues they sampled, and you can see on the simple bar graph above, patients numerically do sample more cues, but they're also sampling them very suboptimally. So for example, here in red, you can see some patients are sampling a lot of 1 or 2 cues. You can't really integrate evidence then, and they're sampling a lot more cues sometimes. And nevertheless, compared to a Bayesian integrator, an optimal Bayesian integrator, they were suboptimal. And in terms of strategy use, it seems that most people, patients and controls, are sort of integrating evidence, but some of them are also relying on the fact that they respond when they get 2 matching stimuli at the end of a sequence. So if you see 2 left mice, you're more likely to make a response than if you see left-right. So sort of kind of ending on a same response, a non-conflict trial. Okay, and so for the LFP and the MEG recordings, I'm just going to go over how I've defined the conflict. I'm calling it same and different. You could call it match, non-match, low conflict, high conflict, depends who you are and what you want to call it. But essentially, within the sequence, for every single cue, I defined whether it's the same or different as the one right before it. So here you see 2 right-facing mice. I would call this cue, which I call QI, a same trial, and this would be a different trial. And remember, I'm doing that at every single time point, except the first and last trials, obviously, where I can't define that. And I'm just going to look at what's happening in the brain. Okay, so first let's look at the subthalamic nucleus. I'm plotting beta power, and these vertical lines represent the onset of the cues. QI is the first point where I define same or different. And what you'll notice is that very early after the onset of this cue, there's a difference between these same and different trials. And what you'll also notice is that even though at first, strangely, beta power seems to decrease, it eventually does increase. So it does seem like this conflict information is carried over to the next trial. And that's more visible here when you look at the subtraction. So there's this first kind of dip in beta power, but then it increases. And we know that beta power increases can be associated with response inhibition. In the cortex, it looks exactly the same. So just for the interest of time, you can just look at these two difference waveforms. They look very similar, but you'll notice two things. In the cortex, the signal starts a little bit earlier, so it seems like the conflict signal may originate in the cortex, and it also kind of completes itself within that first match or non-match cue, rather than carrying over. And when we look at where the signal comes from in the brain, we find that there's occipital, temporal, and frontal sources where this sort of conflict signal arises. And then in order to kind of understand the interaction between these brain regions, we looked at coherence. And here I'm just plotting time frequency plots with coherence frequency on the y-axis, and then 0 is the onset of the cue. And you'll notice very nicely that the frontal cortex and the right subthalamic nucleus show an increase in coherence when there's a conflict. So that means these two brain regions are communicating when there's a sort of conflict detected. And if you want to look at it more specifically, you can see it's in this kind of low beta band. You get a really nice peak and difference in coherence. And some of the more keen listeners will think, why? She said that there was a decrease in beta power. And yes, I did say that. There is a decrease in beta power, both in the cortex and the subthalamic nucleus. Nevertheless, in beta power, there's also a coherence increase. So summarizing that here, this is extremely busy and we don't have time to go over it, but just the gist of it is coherence between the areas increased, and power itself, both in the frontal cortex and the subthalamic nucleus, is actually decreased during this initial time period when the cue comes up, when you would have that conflict. Some of you may be wondering why I banged on about accumulating evidence and then looked only at local conflict, which seems really boring. The answer is because we actually did look at different models of evidence integration, and we found no evidence that the subthalamic nucleus does any sort of normalization, evidence integration, or any sort of stimulus number, which I call here urgency signal. So basically, there was no evidence that there was any sort of surprise signal or sort of expectation violation in the subthalamic nucleus. Obviously, we do integrate evidence as humans, and we know the patients and controls did it as well. So we also looked at our whole head MEG data, and we found that indeed in the beta band at the cortical level, there is evidence of some sort of evidence integration. So we are integrating evidence, but maybe not in the subthalamic nucleus. So quick summary, patients sampled more cues, but they were still suboptimal. We found beta power to be the signaling of conflict. I didn't show any theta results because they weren't there. So the kind of classic idea that theta is signaling conflict, we were not able to replicate that in this sort of different task that looks at evidence accumulation across time. Beta power starts earlier in the cortex for conflict. It's more prolonged in the subthalamic nucleus. There's an increase in coherence, and there's no integration, evidence of this integration or surprise signal in the subthalamic nucleus. And really just being hopeful, we think that this pathological amplification that we saw in the subthalamic nucleus, so this carryover of this conflict signal, might be something that leads Parkinson's patients to have more impulsivity or motor impairments. Very speculative. Nevertheless, thanks very much to my supervisors, Vladimir and Rafal, and to you for your attention.
Thank you very much for the talk. There was a lot of information there.
No, sorry.
No, that was cool.
I have loads of extra slides with other data if people want to see it. So,
I mean, I would like to, because I'm not an expert in the topic, but it was very clear, I think. So yeah, we don't have questions from the audience yet. I found particularly interesting. There we go. We have a question, so I keep mine for later. So this is a question from Alisa Moore. Does the data on cortical STN coherence point to involvement in the hyperdirect CT basal ganglia pathway as opposed to the indirect pathway in this conflict behavior? And she's saying both have been implicated in motivated behavior and impulsivity in animal models.
So great question. And in the preprint, we do have a little discussion about the hyperdirect pathway and how that might be involved. Indeed, there is some evidence that sort of this lower beta, which is kind of what we're finding, might be indicative of this hyperdirect pathway. I don't have any sort of DTI data or anything else on these patients in order to kind of look at sort of connectivity and things like that. But in the little QR code in the corner, you can maybe go look at our preprint and see what we said about it. But this isn't really my background, so I'm not going to say anything more than that because I'm not sure I can answer it properly.
Cool, thanks. And I think if you are not scanning the QR code, it's the preprint on bioRxiv, right?
Yes, yes.
I'm copying that again in the chat. So I was about what I found most interesting. So this connection between the coherence between the subthalamic nucleus and the frontal cortex. Could you go back to that slide?
Yeah, sure. This one. Sorry, this one.
Yeah, exactly. So could you say a few more words about this, or how that?
So there is like really a handful of studies, obviously, because these are patients. You can imagine there aren't that many studies on the subthalamic nucleus invasively anyway. And a couple of studies have looked at sort of what's actually happening, and because a lot of the sort of healthy neuroscience shows that the cortex does all this great Bayesian integration, but then there are all these models of the subthalamic nucleus that claim that it does some form of normalization or something along those lines. So that was why we designed this task. But it turns out that really the only thing we can find is that the frontal cortex, which by the way, it's MEG data, so pinch of salt, but it actually was localized to BA6, so supplementary motor area, rather than the inferior frontal gyrus, which is often more involved in these stop signal go, no go tasks. So that was a bit surprising, but again, no one has ever looked at it with sort of MEG where we could actually source localize. So this is the first bit of evidence that maybe that like a more superior frontal area would be involved. And indeed, what we find is that when there's conflict, these two areas are communicating more. So I think that kind of makes sense. It's a little bit disturbing that it happens in that time window when the Q is actually up, but we'll see what the reviewers say about that. But we couldn't really find anything that would indicate that that would, diminish the results necessarily.
Thank you. Maybe there are questions from the other panelists? No? Okay. So what do you keep working on this or?
Yeah, I mean, my background's actually the hippocampus and memory. And this was sort of I've always really wanted to work with deep brain stimulation patients. So this kind of happened randomly, but it actually has led me to want to study the subthalamic nucleus a little bit more, not just from this sort of decision-making or conflict detection purpose, but maybe its involvement in other circuitries in sleep and memory consolidation. So that's why I kind of said, I'm sorry about the question about the hyperdirect pathway. I just don't feel comfortable enough talking about that necessarily. But this data is actually available online, both the MEG data and the LFP data and all the scripts. So if anyone wants to play around with it and find something else, that'd be really cool. I did really beat the horse or whatever you call it. Really did try to get everything out of this data that I could, but there's probably a lot more in there to look at. And I didn't show any of the behavioral modeling we did on the patients and the controls, but essentially the idea was that we would look at this sort of testing this model of Bayesian normalization in the subthalamic nucleus. And as I show here, there is really no evidence for that. So I think one of the benefits of, science, or rather this study specifically, is that the senior author was the one who came up with the model, and we didn't find evidence for it. So it's kind of good to update those models of decision making, I think.
Cool, thanks very much,
Thank you.
Zita. Anybody said anything?